Federico? Federico?
Federico?
Sì,
Sì, lo vedo.
Venga, ponga, ponerse los auriculares para que lo escuche.
Federico?
sono qui.
Senti, guarda, qui c'è un piccolo disguido, se c'è alle 10 come ti ho mandato, alle 10:20 non mi risulta il qui. L'ora iniziale sarà fra pochi minuti. Suppongo che alle 10:20, tanto quella delle 10:20 per un buon disguido, no, perché c'è un problema che c'è un bebè, non si connetterà, quindi diciamo poi si riconnetta con Srivastava e schioppa immediatamente dopo. E quindi aspetta un momento e fra poco mi connetto da un altro apparato, non da questo, e andiamo avanti. Abbi pazienza un momento, scusa.
Sì, vabbè, non c'è problema.
No, grazie.
No va a transmitir de allí, va a transmitir de allá. Sí, perfecto. Va a moderar bien.
Good evening, Federico. Thank you very much for accepting our invitation. First of all, I have to apologize for a number of problems which arose, which affected mainly few sessions. In general, the organization went very smooth, but a few sessions had a problem on Wednesday morning, and these sessions were reported to today. And to this were added the very few cases as yours, in which there was to make a change with respect to the previous program. As you may appreciate, there will be very few people connected, but this is not, I mean, may appear to be a serious problem when talking, I understand, but will not be that, considering that this presentation is going to be recorded and it will remain online, and our purpose is more than making the presentation available immediately, to leave it available for young physicists who want to learn something about that. Therefore, I think now is 10:13. You can start talking, and you have in principle 20 minutes, but since the next talk is foreseen to take place at 10:40, even if we extend a few minutes, nobody would cut your talk. Nobody means I'm not going to cut your talk. Thank you, Federico. Please start. Wait a moment. I have to. You can, without any problem, upload something for the screen. You have already been authorized, so you can.
Okay, thank you. I just started screen sharing. Actually, according to the, sorry, wait a second. According to the last program you sent me, I was supposed to start at 10:20. So I was ready at 10, but according to the last program you sent me, there was going to be a break between 10 and 10:20. I don't know what that.
There was some problem for that, some misunderstanding for that.
Yeah,
but
anyway, we're here and
we have solved
no
anyway with the next talk, because Dr. De Pino will not talk, so therefore makes no difference.
All right, that's fine. So thank you for the invitation, and I'm sorry I'm not there in person, although I realize that, yes, through a recording, in theory, we can reach a lot more people. But I've never been to the Dominican Republic, and so it would have been nice to visit. I suppose we'll have to postpone my visit in person until sometime after the pandemic is behind us. So I'd like to share some of our work on multifunctional materials for emerging technologies. By training, I'm a physicist. I started working originally on the surfaces and interfaces, the properties of materials at the nanoscale. And then for various reasons, I started working on more applied problems, including biomedical materials, energy technologies, photonics, aerospace materials, and so on. So today we are confronted with some major challenges that we need to address if we want to promote a long-term sustainable coexistence of all living species on the planet. The United Nations have identified 17 major challenges called the Sustainable Development Goals. And in the past few years, I've decided to reorient at least part of my research to see to what extent we could contribute as academics to addressing some of these SDGs. So I've underlined the ones that I think I can in principle contribute to. Number 3, good health and well-being. Number 4, quality education. Of course, as an academic, that's always my priority. Number 6, clean water and sanitation. Number 7, affordable and clean energy. Number 11, sustainable cities and communities. Number 12, responsible consumption and production. And number 13, climate action. But the one that I consider most important of all, for a number of reasons, is the energy challenge. And you see here from these two graphs. These are borrowed from a paper in Physics Today from 2007, but they're actually still very accurate 14 years later. So over 80% of the energy we use is based on fossil fuels. A few percent originates from nuclear, a couple of percent is hydroelectric, and the renewable technologies like solar, wind, geothermal, tidal, biomass, they only make up 10 to 15% on a global scale. And this is a serious concern. We really have to completely change this proportion if we want to find a sustainable path. And what makes it even harder to actually shift towards renewables is the graph on the right, which shows world population as a function of time. So if we go back in time a few hundred years, world population was much, much smaller than it is today. And it was growing very, very slowly, or it was roughly constant. For a long time, it was less than 1 billion people on the whole planet. And it's only around the 18th century, the era we refer to as the Industrial Revolution, that we started growing in numbers quite drastically and rapidly. We reached 1 billion, and then within 200 years, we're almost at 8 billion people on the planet today. And that's because world population increases at a rate of 200,000 people per day. That means roughly 70 million per year. So that's like twice the population of Canada that suddenly pops up on the planet every year. Or twice the population of California, or a bit more than the population of Italy. This also means that if you wait about 15 years, you have an extra billion people on the planet. So in less than one generation, it's like having a whole new country the size of India in terms of population that has popped up on the planet. And of course, you can imagine more people want more energy, they need more food, they want more water, they need all sorts of health services, and they will produce a lot of waste. Hence those SDGs that I mentioned that are more and more urgent to address. So from these two graphs, you will have noticed that the energy challenge, and indeed all the sustainable development goals, they're not just scientific challenges, they're much broader and more difficult to address because they also involve politics and economics and policy and so on. So this is why the energy challenge, I've decided to see if I can address it through a somewhat different and more global approach. UNESCO, the United Nations Educational, Scientific, and Cultural Organization, has a program called UNESCO Chairs. These chairs are networks in which participating organizations pool resources to address pressing challenges and contribute to societal development. Ideally, a UNESCO chair would address one or more of the Sustainable Development Goals. And so these chairs are supposed to act as think tanks and bridge builders between academia, local communities, research, and policy making. And so ideally, we want to inform policy decisions because that's what's really going to shift gears in addressing renewable energy technologies and climate change and all sorts of other pressing issues. So the overarching objective of our UNESCO chair is to obtain access to sustainable energy for all, or if you like, SDG number 7, clean and affordable energy. Of course, our goal as academics is to build capacity, especially in developing countries. We have over 30 partner organizations in more than 20 developing countries. And essentially, we built our program around visiting professorships and student exchanges, organizing international workshops, delivering web-based courses, and offering a handful of scholarships from PhD students, highly motivated and promising PhD students from developing countries. So due to the limited time that we have today, I will share with you only part of the research program of the chair, a snapshot of what we do in terms of materials for energy conversion, focusing mostly on solar technologies. The challenge here is to absorb as many photons as possible from that distribution of photons that hits planet Earth from the sun every hour of every day, and transform these photons into another usable form of energy. And to this end, we mostly focus on these photoelectrochemical solar cells. These are essentially low-cost, low-energy intensive technologies that mimic the photosynthesis reaction in plants. The original concept was developed by Gretzel about 30 years ago. He invented dye-sensitized solar cells. This technology is still considered very promising, but it has limited efficiency and especially limited stability. Now, we've decided to change the dye component in these cells with quantum dots. These are semiconductor nanocrystals in which the energy levels are discrete, similarly to an atom. So the confinement in this very small volume of the semiconductor nanocrystal allows us to actually tailor the optoelectronic properties and tune the band gap by changing the size, shape, and composition of the quantum dots. One important aspect of all renewable energy technologies, and in fact, the challenge that is common to all of them, is that they're intermittent. This means that renewables do not provide a continuous source of power. If you consider wind power, well, wind goes in cycles of about half an hour. If you consider solar power, well, during the day you have it, and during the night you have nothing. And on the other hand, even during the day, when a cloud passes overhead, your power will drop drastically. So it's really important to develop, in parallel to these renewables, adequate energy storage technologies, because storage is the common challenge to all renewables. So one interesting way of using solar energy is essentially to split water into oxygen and hydrogen, so that hydrogen can then be stored and later used as a clean chemical fuel. The reason is that about 2/3 of our planet are covered in water, and when you combust hydrogen in a fuel cell, the only byproduct is water. So basically, this would make a clean, environmentally friendly cycle. And so part of our research consists in using solar photons with photoelectrochemical quantum dot based cells for hydrogen production. So here you see the concept is that the photoanode is made of a wide band gap semiconductor, most typically titanium dioxide, or it could be zinc oxide, tin oxide. There's various candidates here. Metal oxides tend to have a large band gap, more than 3 eV, and this is not conducive to absorption of many photons, because a semiconductor can only absorb photons with energy higher than the band gap. And photons with energy higher than 3 eV are in the ultraviolet region of the solar spectrum. Now, in this region, there's only about 4 to 5% of all photons that come to planet Earth. So basically, this means giving up on 95% of usable photons. To actually absorb more photons, what we do is we decorate the titanium dioxide, the metal oxide, with these quantum dots. In Grätzel's original concept, he used dye molecules. These are large organic molecules that absorb in the visible infrared and near infrared parts of the spectrum. You can replace them with these quantum dots, and as I mentioned, these have energy levels that are size, shape, and composition tunable. So we've made quantum dots with different architectures. In this case, you see here a core of lead sulfide and a shell of cadmium sulfide. This allows us to precisely tailor the energy levels and optimize the band gap, leading to a photocurrent density of 11 milliamp ampere per square centimeter and 110 milliliters per square centimeters per day of hydrogen generation. So this was a world record for hydrogen generation for this type of photoelectrochemical cell. Since then, we've actually perfected the cell, made it more stable, and improved the performance in other ways. Now, from those core shell quantum dots, you can imagine that one of the issues is that they contain lead and cadmium, which are toxic elements. So one direction which we decided to move into was to make colloidal quantum dots that are heavy metal free, that do not contain any heavy metals. So essentially, we do not want to include toxic elements like cadmium and lead. So we ended up making these quantum dots with a core of copper indium selenide and a shell of copper indium sulfide. Both the processing is based on green chemistry, and the final product is also made of non-toxic elements. So we succeed in making these quantum dots, and we make the photoelectrochemical cell using these as photoabsorbers that sensitize the metal oxide. And of course it works, but the trade-off is that we obtain a much lower photocurrent density, in this case about 3 milliampere per square centimeter. So we lose about a factor of 4. So this is one of the trade-offs we have to be aware of. Unfortunately, so far, it seems that the best performing elements in terms of composition of these quantum dots are often toxic elements like lead and cadmium. So we have to find a way to actually eliminate the toxic elements so that we have a greener material, but still high performance. Another technology that we're working on that is very promising are these luminescent solar concentrators, or essentially also known as solar windows. These are particularly interesting for building integrated photovoltaics, which means you have to imagine a very large and tall building, and you want to use the area of your windows to partially power the activities in your building. Now, if you place a conventional solar cell in front of your window, it is not transparent, and so you wouldn't let any light in, and so this would be counterproductive. So basically what you do instead is you place in front of the window an organic matrix, a waveguide that is made of a transparent polymer, and all around this waveguide you place very thin conventional solar cells, and inside the waveguide you will disperse chromophores that can absorb radiation and re-emit concentrated light at longer wavelengths. So most of the photons go through the waveguide and illuminate the building itself, and part of the other photons will be absorbed by the chromophores, re-emitted, and will then hit one of the solar cells at the edges. And this allows to power, as I mentioned, some of the activities of the building with a very low-cost approach on a comparative basis. So one of the key parameters here is to engineer the Stokes shift of these chromophores. The Stokes shift is essentially the difference in wavelength between absorption and re-emission. You want it to be as large as possible so that you minimize reabsorption events. And again, the same quantum dots that I mentioned earlier with a core of lead sulfide and a shell of cadmium sulfide are the best performing materials for this purpose. Now, what's interesting though is that also in this case, we've developed greener approaches and greener materials, and the latest generation of dots are actually carbon dots. So these solar windows are eco-friendly, and the carbon dots are made mostly of carbon with a little bit of hydrogen, oxygen, and nitrogen. These are the 4 most abundant elements on the planet. So in terms of sustainability of the source, it couldn't get any better than this. In principle, these elements are also non-toxic, although it is also known that any nanoscale system could in theory be toxic. But anyway, we obtain very good performances also in the case of carbon dot based solar windows. And so this is another promising direction. So at this point, I guess this leads me to some conclusions. We study a variety of nanostructured materials. We're interested in properties that arise at the nanoscale due to size effects, quantum confinement, different surface to volume ratio compared to the bulk. And in particular, we're interested in understanding structure property relationships in materials, focusing on nanoscale materials. So the surfaces are the most important aspect here, because in a nanomaterial, you mostly have surface and you have very little volume. And we use these nanomaterials as building blocks for a variety of technologies. A huge proportion of what we do these days focuses on energy technologies, in particular renewable energy technologies. And today I shared a little bit of our work on 3rd generation solar technologies based on quantum dots. Quantum dots are semiconductor nanocrystals in which the optoelectronic properties are size, shape, and composition tunable. So we do quantum dot solar cells. I didn't have time to discuss that, but we also make photoelectrochemical cells for hydrogen generation using quantum dots. And finally, we use these quantum dots as chromophores in solar windows. I owe a debt of gratitude to the funding agencies that support us, in particular from the provincial government of Quebec and the federal government of Canada. And then we've worked in partnership with over 20 R&D Canadian companies. They're mostly listed here. As you can see, we collaborate widely all over the world, significantly through the UNESCO chair, but also through other avenues. I've co-authored papers with colleagues in 36 countries, and I've actually trained a new cohort of young scientists. So 28 former group members are themselves now professors in 14 different countries. And I thank you very much for your attention. I want to emphasize that the concept of the UNESCO chair is very inclusive. So anybody who wants to participate in our activities is most welcome. So if anybody wants to reach out and propose some form of collaboration, we're very open to this. Thank you very much.
Doctor, debe activar el micrófono, doctor.
My microphone is still active. I don't know if you're talking.
Excuse me, Federico.
Okay.
Thank you very much. I was not connected there. For some reason, you've been more brilliant than Yogi and Schioppa, who claim that they are unable to enter the Sala C. Now, can I ask you a favor, Federico? You have the email I sent to you. Can you send the email to Schioppa and the Yogi and see, because I don't have from here easy way of sending the email. Can you tell them that you entered what is the problem and you try to help me from there?
Yes, but I don't know if I have their email addresses. Wait a
Yes,
second.
they are, because I sent to all of you. The next one,
So you want me to resend the same email?
to contact them by email and telling them that you have been able to talk and to understand what has been their problem.
Okay, who do you want me to send it to in particular?
Also, Yogi Srivastava and Marco Schioppa. You can write in Italian because they both speak Italian.
Okay. Yogi Srivastava and Marco Schioppa.
And sorry for you asking you this favor, but it is
No
the
problem.
faster way.
Marco entered the room.
Marco is just entered. So try to contact Yogi by email, please.
Yeah, I sent to both of them. It's sent now.
No, I don't see Yogi. I see only Marco, not Yogi. Marco, benvenuto Marco. Welcome. Now I'm going to help you.
Hi, Leo.
To if you want to put some if you want to put something in the screen, I must authorize this. Devo autorizzare sto poner pantalla. Siamo. Ok, it's authorized. Okay, Marco, you are already authorized to share. No, Marco, that's fine. Giusto.
No, it's nice.
Marco already can put something on the screen. Federico, while Marco is talking, can you try to understand with Yogi what is his problem? So I start with Marco and put Yogi immediately after, because at 10:40 was supposed to talk Gabriella De Pino. Gabriella cannot join us, and therefore we can anticipate the talk of Marco and leave that of Yogi in 20 minutes from now. Marco, thank you very much for joining us, accepting the invitation. As I was telling Federico, for a number of reasons, this session is a bit complicated. There are very few people attending it, but this is not a real problem. I mean, in the long run, it's not a real problem. In fact, we are recording the talk. It will remain it will remain on the web, and so many other students will be able to see this. So please go on and start.
Okay, can you hear me?
Perfectly.
Perfectly. Okay.
Speak louder, please, but we can hear you.
I try to speak louder. Okay. So I would like to tell you about the activities in progress in our university. This is the same university where our chairman worked for many years. Leo, can you mute? Okay. So, first of all, an aerial view of the University of Calabria is a very nice university, many buildings aligned along the bridge. So this is more or less 1 kilometer long. And into the dashed circle, I just indicated where is located this energy or nuclear and subnuclear physics laboratory. This laboratory, just to introduce it, the laboratory has many halls. The main is what we call assembling and storing area. Is a very big area, and there are other laboratories and clean rooms. And here I just also indicated that the team, there are many PhD students, many students and researchers. Okay, start with these activities. The first one is the the atlas at LSC. We work inside this collaboration since many years. We can say from the beginning we participated to the design of the detector and mainly to the construction of the muon spectrometer. The last item we are participating is the so-called New Small Wheel project, is the replacement of the two first forward station for the muon spectrometer. They will be included during the phase 1 of the LSC upgrade. It means this year, the end of this year. You can see on the bottom right, the wheel is named small, but it is 10 meter high and 10 meter wide. So just to distinguish the small from the big one is 22 meters diameter. On the bottom left, you can see the hole where these two wheels are in preparation. One is ready, and the second one will be ready in the next year. So what we did in this project, we built a part of this project. It is named micromegas detectors, are the very innovative micropattern gases detectors. One of the most promising, but this is not a really easy task, because it was during construction of very large sites detectors. We met many problems, and we tried to solve it, and now the detectors seem to be ready. Of course, seem to be, because the certainty will be just at the end when the will.
Marco, si sente molto fioto. Non so se non puoi parlare un po' più ad alta voce, un po' più vicino al microfono.
I am just attached to the microphone, so okay, I'll try. So I was saying this. We are involved into the micromegas detectors, where we built a part of this detector. The detector was built in 5 sites, one in Greece and one in Russia, in Germany, in France, and Italy. The Italian consortium was the INFN, Istituto Nazionale di Fisica Nucleare. So inside this consortium, we had the responsibility to build 1/4 of this big project. So we had a responsibility inside this project for what concerned the construction of the cathodes of these detectors. And it took more or less 3 years for this to completely the construction. The next, and this is what we will have as a next project, is the RPCBI. It means that we will put inside the muon spectrometer, the barrel of the muon spectrometer, another trigger station. It will be located in the inner part, can you, probably you can see this parallelepiped, blue parallelepipeds. They are the tracking and the trigger chamber together. And at the present, we have just 3 stations. One is located outside, and the other 2 is in the middle part of this barrel. And we, the project will provide the new RPC, so a new trigger station in the inner part. So the inner part is the cylinder, the internal cylinder of this detector. So what we'll do, in practice, this detector is a sandwich of a gas gap where the gas is located and where the high voltage is applied. And there are 2 panels for the readout of the signals that we name readout strips. And we will build in our laboratory 1/2 of the total of the panel that will be built. Okay, we go ahead. This is for what concerns the outreach activities, because in parallel to these activities, we have many activities for the outreach. One is more promising, is that I show here. It is a commercial card based on Arduino 2. The shield is named Ardu SIP. SIP means silicon PM. So the small tile 5x5 or what you want is a readout by silicon PM from a Mamatsu, for example, and then this signal and the high voltage is sent to this card, and this card provide the acquisition of the hits, but also can give you an analog signal that we can see on the scope and then characterize this detector. What I show here is a measurement that this is in progress in the lab. This is a student is making his thesis, is the reproducing of the Rossi curves. It means that we collect data with a different absorber, thickness of the absorber on top of this detector, and just to reproduce this curve. The bunker is in lead, and we have recorded at the present 5 measurements, 1, 2, 3, 4, and 5 centimeters, and we are observing the increasing first and then the decreasing in the rate of this counter, as expected by the Rossi curves. Another activity is also something that we can make is the tracking device. In sense, as you can see here, another student, this is preparing his thesis in our lab, is a detector that it is the same that I just shown you before. This detector is mounted into the shoulder, and you here in this case the guys goes into a mountain and recorded the counter and the altitude in order to reproduce some changement in the rate due to the altitude. So also in this case, data are under processing because it was recorded last week, and then it will take some time to process and give the last results. Another activity is always with the same detector, another detector. We have 6 in our lab, is to investigate the rate of the particle, the cosmic rays inside under the lake water at a different depth, from 1 to 5 meters. Also for this case, there is a thesis for another student, and the aim of these experiments is to reproduce the Domenico Pacini result that we made in more or less 1 century and 10 years ago. Characterization of the scintillator counter using external telescope, and this is another part of this the activity of the lab. Now is something that we need before starting any use of the detector. And in this context, I would like to mention a measurement that we are doing with a couple of scintillators in coincidence put over an absorber to measure the negative muon lifetime. As you know, the muons of the cosmic ray will stop in the matter, and when it is at rest, it can be captured by an atom, and its orbit is very close to the nucleus. So if the nucleus is very heavy, the orbit is the muons spend a lot of time inside the nucleus, and then can be captured by the nucleus, and then decay is not possible, in the sense it will disappear. This is for the negative. For the positive, there is another process. The positive can capture an electron and form the muonium that can and it can decay as a free particle. In the muon, in the negative case, the muon can be captured and then removed from the statistics. Then we can see some difference in the time decay spectrum from one to the other. This is the case of the decay of the muon, positive or negative, where the electron can be emitted towards the 2 scintillators, and then we can observe, as I can show in this sketch on the right, the signals formed by the 2 scintillators. The first on the left, the first signals on the left are the due to the muons that pass through the 2 scintillators and gives the signals, and the second one, the second couple of signals delayed by this decay time is due to the electrons. So when this occurs, this time is recorded, and then the data are analyzed. This is a simulation of all the conditioning and data acquisition program. This is just a picture where you can show you the couple of scintillators over the absorber. On top there is a lead, blocks, bricks, and on bottom you can see iron sheet. What I would like to say for this experiment, we have analyzed and we will continue to acquire more data in order to increase the statistics and then reduce the statistics errors. But we would like also to modify slightly the setup in order to reduce the systematic errors due to the component of the background that is that affect this experiment. The last topics, but this is not the least, is the study of eco-friendly gas mixture for RPC detectors. The European Union restriction asked for the reduction of greenhouse gas emissions into the atmosphere, and we can try to reduce it recirculating the gases, but part of these gases must be furnished because the detector are not completely tied to the gas. So we have a very big problem because many RPC detectors are using gas mixture with the very high green warming potential. This is greater than 1000. And you have to consider that the unit is the CO2. So if we can consider CO2 a greenhouse gas, you have to think about what can do a gas with 1000 more potential. So it is necessary to replace this component. Normally, we have tetrafluoroethane inside the gas mixture, and we would like to change, to replace this with some eco-friendly gases. So possible candidate is this HFOZE, is an hydrofluorolefine gases with CO2 or with helium. So the experiment tests are ongoing in Cosenza. I don't have to present any data to present, but in the next future it will be possible. This is the setup we have. There is a gas mixture with many 4 bottles of gas with different gases, CO2, tetrafluoroethane, HFO, and helium. A couple of scintillators will provide the trigger, and then with a digitizer we'll read the signals coming from a tower of RPC. So this is all from my part. Thanks for your attention.
Thank you very much, Marco. Now, I think that we have been unable to establish a contact with Yogi because for reasons which escape to me.
Hello, hello.
Ah, Yogi?
Sì, sono qui.
Okay, so since Yogi at the very last moment was able to reach us, I'm not going to close the session.
No, no. No.
In fact, no, it was a very complicated thing to put Jordi in connection with us. So first of all, Jordi, welcome for your patience and your ability to join us. Second, I would like to tell you what I told already to the other people. As you may see, we are very few people in this session. This is due to two different reasons. These sessions, all the sessions of Saturday, come from difficulties we had in the organization. So, in a sense, the way
this is the person who just spoke.
Okay, find your thought.
of solving problems which arose during the organization. Therefore, this should not make you feel to talk to the void, because the main point is that we are recording these talks. And the records will remain in the Congress, available to everybody, so that really what you are going to say and tell us will be useful for other students in the next few months or even years. So, Jordi, thank you very much, and now you can start if you want. Do you have any problem? I don't hear you. Jordi, I don't hear you.
Can you hear me?
Now, yes.
Okay, just give me 30 seconds that I get my PowerPoint.
Okay, so you have been already authorized to upload your slides, no problem.
Okay, but I don't see my PowerPoint here. Do you see it? Here is my PowerPoint.
Okay, then open it.
Okay, 1 second. Open recent.
No, don't worry, Jordi. We are here. The people who are watching you, we are all old friends, so that you can take your time and don't have any problem with that.
Now, go and do the.
Okay, can you see this?
Okay, make it.
What
go
do I?
on slideshow.
Slideshow. 1 second. Okay.
Lo vedono adesso?
Now you should be able to see, right? Can you see me?
No, I see Leah. Not.
What happened here?
Take it easy.
Huh?
Do they see it? Talk to them.
Yeah. What did I do here? Because I can see my my screen, but that's it.
But
On
you
the
could
bottom, you
share
can
screen.
Yogi, on the bottom you can see a bars with the microphone, the camera, and also a button with the share your screen.
Okay.
It's a screen.
Yeah.
It is the only.
Yes, it's here.
Okay. You push and then choose your file. Okay, good, very good.
Okay. Can you see anything?
Go here and
everything.
Okay. So I'm sorry, I'm pretty bad at this stuff.
See it?
Can you see my file?
Yes.
Leo?
Yes, we can see.
Okay, so the object of my talk.
I can see you, sorry. I did not answer because the technician had put mute my microphone. But yes, we can see everything.
Okay, so now can you see it? Leo?
Yes. Yes.
Okay,
yes.
So this is a method to ablate various types of viruses in open places. Okay, so this is the title, and we have been doing this work for several years with an student now, a colleague, Sassaroli, and two people from Northeastern, John Swain and Alan Widham, and Meenakshi Narayan, who is a big shot in the CMS at CERN, and George de Montmollin, who is a Swiss engineer who has helped us in doing many of these things. So, okay, now all the details you can find in this link, which I have put here, and it is called non-chemical signatures of biological materials. And the idea was, what sort of frequency should you be listening at from COVID-19? So just like our computers, when if you have enough memory, our early computers, we had to connect it by a wire, by a modem. Okay, it was exactly the same for evolution as it came in. The single cell objects that first developed, they had a single frequencies and they were just connected. Is it as if, okay, like a modem? And that's how they used to communicate. Then as evolution progressed, then they became wireless, just like we are. Right now, I don't use a modem. Don't you? You don't either. And so, and what are we using here? That every single life form has a unique vibrational frequency. It's just like what you find in atomic spectrum, the nuclear data table, or the compendium of hyperfine structure. So what we said was that while all the great activities, which have been exceedingly successful in one regard, from vaccines and so on, but they are all based on chemicals. So our idea was that just like the Genome Project, which is a purely static biochemical catalog, should be augmented with a catalog or register of the frequency spectrum of basic living forms. None such exists. People, researchers work on this one or that one and so on. They study, they find it, but there should be, it should be just like the Genome Project, where you have all the DNA and RNA structure already done. Okay, so these may provide, because as we will see, especially for mutations, the frequencies change. Okay, and because the frequencies change, this is, if we could listen to it, you see, we could actually have what we call asymptomatic and so on. Namely, the chemical means are not yet refined enough to be able to do that. And so this was our point of attack. So I already said every life form is endowed with sonic signals, sound waves. And so the way, as you might imagine without doing any computations, that it depends on the conformational geometry of the object, how it's going to, at what sort of frequency it will emit radiation, sound radiation. Okay, so for example, if you take influenza A virus, which has a radius of about 90 nanometers, it's spherically symmetric, and that has a peak frequency of 8.2 gigahertz. Okay, and the width of the resonance, if you like, or the frequency band is, of course, depends on the pH. In other words, under what ambience it is embedded in. On the other hand, there is a WSSV, which is a rod shape. It's called a white spot syndrome virus, which I'll discuss a little later because it has practical applications. Okay, that is much bigger. It is 300 nanometers. It's like a little ruler stick. Okay, and this is very dangerous to marine life. Shrimp, crab, crayfish, etc. And it has a peak frequency of 6.4 gigahertz with a width for the ones that had been measured, it was about 1 gigahertz. Okay, so now what is the point about resonant signal? I don't have to tell this crowd, which are experts in resonances and physics in general, that the power you will consume in order to ablate something will be much less because you're sitting on a resonance. I mean, it's obvious, okay? But it can be a very large factor, as we will see, okay? So now the problem is almost identical for cancer cells, which is the other thing we have been studying for several years, because if you take a normal cell and watch it, and for whatever reason, it become a carcinogenic cell, you see its frequencies, it's a little softer, so the frequency changes. And there has been a beautiful set of works done basically in the United States, and we are doing some work of our own, where by seeing that frequency difference, you can beam microwave power, because it happens to be, as we will see, that's the frequency range of interest. You see, you can kill the cancer cell, but not harm the normal cell. Whereas, what is the usual problem with radiation therapy? Because radiation will kill the one that you want to kill. But of course, radiation doesn't distinguish between a cancer cell and a normal cell. That's why people lose hair. That's why there are all sorts of inflammations and so on, because it is not specific to the type of cell. Frequency is one thing that does distinguish one from the other because the conformational geometry is different. Okay, now the way you do it is obvious. I don't have to explain to this crowd, so I will go very fast here, which is what you want to apply is you apply, say, an electric field with a peak frequency or a band of frequencies that you are interested in to beaming, and then what you have is that if it is sinusoidal, which is a frequency matched, when it matches that of the specimen you have put in, okay, of course, the power absorbed is much, much bigger. And as you can see, since the force that you apply is proportional to the charge times the electric field, the bigger the electric field is, the bigger the force is. And if the force is big enough, of course, you're going to kill it, because you will rupture the cell or whatever it is that you are trying to rupture. It's a completely general method that applies to bacteria, it applies to cells, it applies to viruses, and so on. Okay, so now I will skip this form because I want to go to, well, there is one thing which has a practical value. Don't worry about the equations I have written, which is the following, that this was a work done exactly 100 years ago by a British engineer called Griffith, and it's now called Griffith's law. Griffith was wondering, how do things break? A building, a big piece of rock for some reason is going to crumble, and so on. Now, the chemist's answer at that time was, you break, for example, look at atomic or molecular level, that you break all the atomic, you break all the bonds, and of course you're going to rupture it. What his point was, that actually you require almost a factor of 100 or so less to do it, because the way it does in practice is a micro crack develops. And then if the situation is bigger and is right, you see the micro crack is what gets big, and then it becomes an avalanche and the whole material drops. And this exactly is what we found when we looked at a given virus that I want to describe to you about. So this has been work started by Yang et al. In 2015. They consider influenza A virus subtype H3N2. By the way, as you will see with my numbers, as I flash them, that as the subtype changes, namely as it mutates, so does its frequency, and by a substantial amount, so that you can have, by listening to it from the outside, you can know without doing a chemical cell test. Okay, so the resonance frequency is about 8.2 gigahertz. Now, resonance here helps because this is in microwave. Now, you don't want to cook somebody. So you want to use IEEE has power standards that you give them the frequency, or you look up the frequency. They tell you how much power you can evolve before damaging human beings or animals or whatever. Okay, so this is where resonance helps, because it reduced from what originally in the 1980s, when people wanted to do it with microwave, they were basically burning this stuff, whatever the specimen was. But doing it with resonance, as you might imagine, you see, you gain a factor of 15, sometimes even 20, and then it is below the safety line. Okay, so this was specifically tested for this. Now, why is it useful? It is useful because if you have an area, for example, look at a schoolroom. Now, what do we do now? We do cleaning with chlorine, we wash hands, we try to clean the air and so on. But what you want is something without disturbing or affecting the persons who will be there, is to disinfect with particular frequency. Okay, so this is the non-chemical way to go about this business. For example, the another variant of influenza A, which is H1N1, that has a resonant frequency of 7 gigahertz, not 8.2. Okay, now yes, I'm just showing you how different these various things are. This is very much, this is H1N1 flu virus is on the right, which is a spherical one, the one that example I gave you, and the rod-shaped virus, which is like for the one I'm going to discuss it's called WSS, the particular one we want to do that. Now, WSSV is the name given by the biologist for whatever bio they are, okay, white spot syndrome virus. And this has been known for a long time in the Far East. It is only recently, you see, that it has been transferred to the major South American shrimp farms in Brazil and Argentina, as shown in this picture. And its story is very similar to what is being rumored about COVID-19. In other words, we don't know who did it and so on. I don't want to get into the politics of it. But the fact is that it is reasonably recent that, and by the way, the testing they do on shrimps and so on, they do it with the PCR test that I will be taking 2 days from now because I have to take a trip. So it is the same. They were doing shrimp. They were saying 9 were negative and 14 were positive and so on and so forth. It's very similar because this virus affects the system just like the COVID does. It's very similar in its, except it is present in waters of certain type. I won't get into the details but this is of interest to major fishing industry because it was never there in the Western Hemisphere, or at least so the biologists tell us, but now there is. Okay. Now, so this is the one that was again was studied also by us, and then the same resonant energy transfer procedure works. Okay, so the method has been well tried, and it can be okay. Now I do want to give you that similar things have been done or being developed for cancer right now as I speak to you. It was started in 2016 by 2 young people, Hayden Cortitz from Harvard University. Then they moved on to Caltech, which is where most of the research on this subject is. And they gave it this very strange name, oncotripsy. Oncology, you know, tripsy is something American. I have no idea what it is, but what is it? It exploits the difference between a normal cell and a cancer cell, the frequency difference. And why is there, because without doing a calculation, if you go to the next, if I show you what they look like, the normal T cell might be looking in various configurations, might be looking like this one, or that one. But you see, these, compare it to what it's going to become once it becomes carcinogenic, okay? And these obviously are going to have different frequencies. So they took a particular one, which is HCCP or something like that, and I can tell you what its name is. It is HCC, and they found a spectral gap. And so they took push from the outside, the ultrasound, this is in the ultrasound region. And so what was their point? They did pulsed. So this is what time duration in the range of 70 microseconds. And the power density is about 0.8 watts, well within the safety regulation, okay, of ultrasound. So power-wise, it's perfectly fine. And what they found was something very positive and something that was highly negative. Now, the positive news first, that they were able to actually kill 95% of cancer cells, because this is being done in a Petri dish or in a test tube, okay, not on human beings. All right, and without disturbing the normal cell. So in this sense, it was fantastic. So what's the catch? The catch is that and this is the same problem that cancer people who deal with cancer have in surgery. Surgery is localized, assuming you have found the right place. And if the surgeon can kill all of them, then of course, that's great news. But it's well known to surgeons and certainly well known to the patients that if even a tiny fraction of the cancerous cell survives, they start to grow with vehement rate. They become worse. They transfer from one place to another. That is the wild type or whatever their name there are for bio-oncologists. And that's disastrous. Well, this is what happened with them. That when they did, they killed most of them. But then they found that very quickly, they started to grow. So what did they do? What does a physicist do? Well, they hit it 1 million times and finally got rid of them. Now, apparently we have a better method this is not the place to discuss it, but there is a way to do this. So the central thing that I want to take you home is that resonant ablation is a very useful procedure, and in many cases, it has already been shown to work. So it is not something pie in the sky, okay? And it's cheap because it's depending upon what frequency you want to deal with, okay? You can, therefore, it is usually either in ultrasound or at worst, it is going to be in microwaves, okay? All right, so I'm not going to, okay. Now, let's look at COVID-19. Now, the one on the right is the very famous picture that all of us have seen, and that probably we are sick of it. We don't want to see it again. This is from University of British Columbia. This is the COVID, the famous B117 mutation of it. And just by eye, you can see this is not the same as the ending of this. And neither is the frequency. Okay? And therefore, it is, so the method I started with should actually be thought seriously for, this is not to cure a given person, because that would be just too cumbersome. But this is to clean up open spaces. so that you don't have to worry about them. Well, you've got my message, I presume. Okay, so but what we wanted to do, what I wanted to do as a physicist and a scientist who has been working in it for many years, is the following: that the method of if you go and look up the literature, it's just individual research. Somebody has looked at this virus, somebody has looked at this bacteria, somebody has looked at this cell, and so on. There is no standard method even to agree upon what's a good way to measure it, okay? Because people just invent their own and so on. So there should be, so we wanted to propose to the World Health Organization that this is a dynamical setup, because you see, this way you are following that life form in real life, how its frequency is changing, and therefore you have some idea, as we know, if you know something about changes in frequency in real time, you are talking about something about the internal dynamics. So it is a piece of information that chemistry is not going to give you. Okay, so we wanted that there should be a catalog like the genome catalog, except it would be a time-dependent, real-time catalog of life forms. Okay, and once you know that, then of course also you can define the appropriate strategy. What's the range of frequencies? What, by the way, pH value changes the width of the resonance. So that again is a helpful parameter that can be tuned in as to what you want to do. Okay, so for example, what does asymptomatic mean? Asymptomatic in real life, in actual practice, means simply the following. It means that we have no chemical way of telling, because the patient or the person is not manifesting. In other words, the immune system is obviously good enough to contain it, but it cannot subdue it. That's why it can transmit. Okay, so we definitely need a device or a way of measurement. One extra measurement always helps in order to open up more insight into a problem. So this, now I will finish here. You see, when I go for a test in a hospital, okay, they put me on a bed, they connect me to this, and they have all these things. Okay, now there are 4 or 5 frequencies we are so used to, we don't even think about. The pulse, the heart. Okay, so that's typically between 0.6 to 2 hertz. Look at the brain waves. Now, of course, you see those charts that are going in, out, and so on and so forth. They have also these beautiful names: delta, theta, beta, alpha waves. And they range between 3 to 30 hertz. Then slightly above 30, they call it gamma waves. I guess coming from physics, that if it's higher in frequency, it's got to be gammas. Okay, so now that chart, the very low frequency chart and the higher one, actually gives fantastic information to the clinician about the status of the general regulatory system of the patient. This is what we would like to propose, that we can extend the frequency spectrum for a virus or a bacteria. It's the same problem as far as physics goes, okay? At much higher radio frequencies in kilo, mega, or gigahertz, as we saw, as the case may be, okay? And thereby, it can provide us as another useful tool of clear benefit for the clinician and hopefully the patient. Thank you.
Thank you very Thank you very much, Yogi. It's very interesting talk, and I'm sure that Marco and Federico would have questions for you.
Yes.
But since all of us, we know very well each other, I think we have ways of contacting you in Rome or Perugia without much difficulty.
Right.
Anyway, I would now, there is the general thanking I must give to you on behalf of the Ministry of Higher Education, Science and Technology, MESIT, of the organizing committee of this 16th Congress of International of Scientific Research, and of the University of Santo Domingo, Autonomous Santo Domingo, and all of the institutions, researchers, and all the people who made possible the realization of this event. I would like to thank you for your participation in the session today, as well as all the participants in the previous sessions. I would like to emphasize, we had some problems in this. In fact, you've been probably the most victimized people in this of this problem. On the average, it has worked better than you may imagine. But anyway, but I would like to emphasize that this gratitude is due to the fact that all the people who have worked in these 4 days are strongly believe that to make science, to make science make sense. And this will eventually produce a better style of life. Concerning you three people, well, you are a very good friend of mine. I thank you very much personally for your kindness of accepting this invitation, also as a personal invitation of mine. Thank you very much.
Thank you.
Bye.
Thank you. Bye.
Okay.